Inside every quiet piece of matter, beneath skin, stone, water, and starlight, there are changes so small that no eye can follow them, and yet so steady that the shape of the universe depends on them. A neutron may become a proton. One quark may lose its old identity and take on another. A nucleus may shift, an element may change, and far away, in the dense white heat of a star, hydrogen may begin the long path toward helium. At the center of these soft, hidden transformations is the W boson, a particle that appears for less than a breath of time, carries charge, alters matter, and vanishes before light can cross the width of a proton. It is heavy, brief, and fundamental. Not a tiny machine built from smaller parts, but a momentary rising of a field that fills the empty places of space. This journey is built for slow listening, for a room growing darker, for thoughts settling into a calmer rhythm. The story moves gently from familiar forces to the weak interaction, from the glow of photons to the short life of the W boson, from quiet radioactive decay to the heart of the sun, and finally into the stillness of quantum fields. Nothing needs to be held tightly. Each idea can pass like dim light across a wall, leaving only the sense that even the smallest acts of nature are connected to stars, atoms, and the silent structure underneath all things. Matter appears still from a distance. A stone rests in the dark beside a path. A glass of water waits on a table. A hand lies quiet against a blanket, and nothing seems to be happening at all. The surface of the world gives an impression of patience. It holds its shapes. It keeps its names. Iron remains iron. Carbon remains carbon. Hydrogen remains hydrogen. And the night moves across the window with no sign of the small changes taking place beneath it. Inside that stillness, nature is not still. Far below the scale of skin and dust, below the soft border where chemistry gives way to the interior of the atom, nuclei keep their own slow histories. Some are stable, holding their arrangement for longer than mountains have stood above the sea. Others are less settled. A neutron inside them may not remain a neutron forever. A proton may not remain a proton in every possible nucleus. A particle that seems fixed can become another particle, not by breaking apart like a stone, and not by receiving some visible piece from outside, but by changing one of the identities hidden inside it. The W boson belongs to this quiet machinery of transformation. It is not present like a pebble inside matter, waiting to be seen. It does not sit in the nucleus as a permanent part of the atom. It appears only when a certain kind of change is taking place, like a brief ripple passing through a surface that was almost calm. In that brief appearance, it carries electric charge. It allows one kind of quark to become another. It lets a neutron become a proton, or a proton become a neutron, depending on the conditions inside the nucleus. Then it is gone. The event is small beyond ordinary comparison. An atom is already too small for unaided sight. A nucleus is smaller still, a dense center where almost all the mass of the atom is gathered into a space that is mostly beyond imagination. The change carried by the W boson happens within a region even smaller than that. It takes place at distances where ordinary images begin to fail, where words like near and far no longer behave the way they do in a room or under the sky. Still, the effect is not small. When a neutron becomes a proton, the atom changes its place among the elements. The number of protons in the nucleus is the quiet rule that gives an element its name. Carbon has one number, nitrogen has the next, calcium has another. A single change inside the nucleus can move matter from one name to another, from one chemical identity to the next, without any visible hand touching it. The change is not loud. It may happen inside a mineral grain, in a bone long buried, in a trace of potassium held in rock, or in a faintly unstable atom drifting through the body of a living thing. The W boson is the messenger of that change. It is easy to imagine forces as pushes and pulls. Gravity pulls a falling leaf toward the ground. Magnetism draws a pin toward a magnet. Electric charge makes hair lift in dry air, or makes lightning draw a pale line across a storm cloud. These forces are felt by their effects before they are known by their causes. They move things, they bend paths, They hold worlds in orbit and atoms in shape. For a long time, that was enough for human thought. Something reached across empty space, and something else responded. Modern physics gives that reaching a different image. Forces are not simply invisible hands stretched across nothing. At the scale of particles, interactions happen through exchange. One particle affects another through a carrier, a quantum of a field, a small parcel of interaction passing between them according to strict rules. The force is not a rope. It is an event. Light gives the gentlest doorway into this idea. The photon is the carrier of electromagnetism. It is the quantum of the electromagnetic field, and it is familiar because it is also light. The pale glow of dawn, the red edge of sunset, the reflected shine on a cup of water, the faint blue of a screen in a dark room, all of these arrive through photons. Yet photons do more than make vision possible. They also carry the interaction between charged particles. Electrons repel one another through the electromagnetic field. Protons and electrons attract one another through it. The shapes of atoms, the bonds between atoms, and the chemistry of living tissue all depend on the same force that travels through space as light. The photon has no rest mass. That absence gives it a very different kind of life. It moves at light speed because no slower path is open to it. It can cross the width of a room, then the distance between planets, then the long dark space between stars. A photon released from a distant galaxy can move for billions of years, passing through the thin regions between clusters, carrying with it a trace of the place where it began. Nothing inside the photon makes it decay on its own. It may be absorbed, it may be scattered. Left alone, it continues. The W boson is another kind of carrier, and its life is almost the opposite. It is heavy by the standards of elementary particles. Its mass is not a tiny adjustment added to an otherwise light object. It is a defining feature. The reason the weak interaction stays confined to distances far smaller than an atom. The photon can carry electromagnetism across vast expanses. The W boson carries the weak interaction only across a vanishingly small span, so small that even the nucleus of an atom is wide by comparison. This is why the weak interaction feels hidden from ordinary life. It does not pull at objects across a table. It does not shine. It does not hold a planet near a star in any visible way. Its work happens in the small rooms of the nucleus, where protons and neutrons hold close together, where quarks flicker in combinations that form the matter of the familiar world. There, the W boson allows a change that other force carriers do not perform. It does not merely transfer motion. It does not merely bind. It changes flavor, the particle physics name for the type of a quark or lepton. A proton is made of 2 up quarks and 1 down quark. A neutron is made of 1 up quark and 2 down quarks. The difference between them is not a wall of complexity. It is 1 quark. When 1 down quark becomes an up quark, the neutron becomes a proton. When 1 up quark becomes a down quark, a proton becomes a neutron. The W boson carries away or delivers the electric charge needed for that change to keep the books of nature balanced. The charge is not decoration. It is part of the transformation itself. In this way, the W boson makes matter less fixed than it appears. The names of particles are stable enough to build worlds, yet not so rigid that change is impossible. A neutron can shift. A proton can shift. A nucleus can move from one element toward another. In the deep interiors of stars, such changes help begin the path from hydrogen toward helium. In radioactive atoms, such changes mark time in the slow language of decay. In the early universe, similar weak processes help set the balance between protons and neutrons before the first light elements form. The scale remains almost impossibly small, but the consequences spread outward. A single W boson does not travel far. It does not linger. It appears in a fraction of time, too brief for any detector to watch directly, and then its energy passes into lighter particles. Often, what remains is an electron, or a positron, or a neutrino, or a pair of quarks that quickly become other particles. The W boson itself is known by these traces, by the patterns left after it has vanished. It is less like a stone found in a field, and more like the passing of a shadow across instruments, built to catch what cannot be held. There is a calm strangeness in that. The carrier of one of nature's four known forces is not a lasting object moving through space in the ordinary sense. It is a brief excitation of a field, arising only when the rules permit, carrying charge, enabling transformation, and disappearing almost at once. Its short life is not a failure. It is part of what allows the universe to have the shape it has. If the weak interaction reached as far as electromagnetism, if its carrier lived like a photon, matter would follow different rules, stars would burn differently, nuclei would settle into other patterns, the quiet reliability of the elements would not be the same. So the story begins inside still matter, where nothing seems to move. The stone remains a stone, the water remains clear, the sleeping body rises and falls with slow breath. Yet inside atoms, at a scale where no eye can follow, the weak interaction keeps its small doorway open. Through that doorway, identity can change. A quark can become another quark. A neutron can become a proton. A trace of matter can take one step into a different form. The W boson is the brief carrier of that step. A force can seem like the simplest thing in the world. A stone falls. A compass needle turns. Dust clings to a screen in a dark room. Two magnets slide across a table until one face pulls and the other resists. And the whole motion appears almost ordinary because the world has always behaved this way. Objects reach toward one another without touching. Light crosses a window. A planet keeps falling around a star. The familiar surface hides the stranger description underneath. At the scale of modern physics, a force is not a silent command sent across emptiness. It is an interaction carried through fields. Space is not a blank stage where particles merely sit and move. It is filled with fields, each one capable of changing, bending, rising, and falling in tiny measured amounts. A particle is one possible disturbance of such a field. A force appears when fields allow particles to exchange energy, momentum, charge, or some deeper property that only becomes clear at the smallest scales. This picture begins gently with electromagnetism, because electromagnetism is everywhere in ordinary experience. It is in the glow of a lamp and in the chemistry of a breath. It shapes the outer parts of atoms, guides electrons into bonds, holds molecules together, and allows matter to resist other matter. The firmness of a wooden table is not mainly the hardness of solid little spheres pressed together. It is the electromagnetic repulsion between electrons in the atoms of the hand and electrons in the atoms of the wood. Touch is already a field, speaking through matter. The carrier of electromagnetism is the photon. In one setting, a photon is light, the small packet that carries color and brightness through the eye. In another setting, it is the messenger exchanged between charged particles, carrying the electromagnetic interaction from one place to another. The same particle that brings the pale gold of morning into a room also belongs to the mechanism that lets an electron feel another electron nearby. The range of this force, from the softness of vision to the structure of atoms, comes from the same underlying field. The photon has a quiet purity in the standard model. It has no electric charge and no rest mass. Because it has no rest mass, no still version of a photon exists. It does not rest in a chair of space. It does not slow into an ordinary particle. From its birth until its absorption, it moves at light speed. Its path may bend through gravity. Its direction may change when it scatters. Its energy may stretch as the universe expands. Yet as long as it remains free, it does not decay from within. A massless carrier gives electromagnetism its long reach. The force weakens with distance, spreading thinner as the space between charges grows. But it never simply stops at a clean boundary. A charged particle still has an electromagnetic field extending outward, weaker and weaker, into distances that become almost impossible to picture. In practice, other charges may screen it. In principle, the range is unlimited. The photon can carry the influence because it does not pay the heavy cost that mass demands. The W boson enters the story as the opposite kind of messenger. It is also a carrier of a force. It also belongs to a field, yet it is heavy, charged, and short-lived. Its presence does not give the weak interaction a wide reach. It confines it. The weak force operates only over distances so small that ordinary atomic space becomes too large a landscape. The carrier cannot travel far enough to let the force stretch through rooms, stones, air, or planetary distances. It lives and fades in the inner scale of matter. The difference between these carriers is not a decorative detail. It is the reason their forces feel so different. The photon's lack of mass lets electromagnetic influence spread outward with no fixed edge. The W boson's large mass turns the weak interaction into a local event, a near contact at subnuclear distance. A photon may pass between stars. A W boson does its work near the place where it is born. It is not a message sent across a cosmic distance. It is a brief permission for change inside the smallest architecture of matter. There are other carriers as well. The strong force, which binds quarks inside protons and neutrons, is carried by gluons. Gluons have no rest mass, yet the strong force does not behave like electromagnetism because gluons carry color charge and interact with one another. Their field forms a kind of binding that grows more difficult to separate as quarks are pulled apart, keeping isolated quarks out of ordinary experience. The strong force has its own quiet severity, holding the nuclear world together with a strength that does not resemble the open reach of light. The weak force has three carriers. There is the W+, the W-, and the Z boson. The Z boson is neutral. It can mediate weak interactions without changing a particle's electric charge. The W bosons are different. One carries positive electric charge, and the other carries negative electric charge. This charged nature gives them their special role. A W boson does not merely pass momentum from one particle to another. It can carry away or bring in exactly the charge needed for a particle to change type. That is where the weak interaction departs from the more familiar image of force. Gravity does not make an apple stop being an apple. Electromagnetism does not make an electron become another particle when it repels a second electron. The strong force binds quarks, but it does not normally change an up quark into a down quark. The W boson belongs to the part of nature where identity itself can shift. It is a force carrier, but it is also the carrier of a change in kind. This makes the word weak slightly misleading. The weak interaction is not unimportant. It is weak in ordinary low-energy conditions because the W and Z bosons are heavy, and that heaviness suppresses the range and probability of the processes they carry. At very high energies, near the scale where these bosons can be created as real particles, the weak interaction no longer seems feeble in the same way. Its coupling is not tiny. The weakness comes from the mass of the messenger and the short distance allowed to it. A helpful way to hear the difference is to picture two kinds of signals. One signal travels easily through open air, fading with distance but continuing outward. Another is so costly to send that it can only be passed hand to hand inside a locked room, and even then, it lasts for less than an instant. The first resembles the photon's long electromagnetic reach. The second resembles the W boson's weak interaction, not because the action matters less, but because the messenger cannot move far from the event that creates it. Inside particle physics, this is described through quantum fields rather than ordinary signals. The electromagnetic field gives rise to photons. The weak fields give rise to W and Z bosons. These fields are not optional additions placed into empty space. They are part of the way the universe is described at its most basic known level. When a particle interacts, the field does not need to become visible in the everyday sense. It only needs to allow a permitted exchange, a shift in energy, charge, and quantum identity according to the rules of the theory. The W boson's exchange is especially brief in ordinary nuclear processes. In many cases, the energy available is not enough to create a full, freely traveling W boson with its measured mass. The interaction proceeds through a virtual W boson, an intermediate disturbance allowed for a very short interval. It is not a little bead flying through a tiny tunnel. It is a temporary contribution to a quantum process, a mathematical and physical bridge between the state before and the state after. Its heaviness still matters, because even as a virtual carrier, it limits how far the weak force can reach. So the path from familiar forces to the W boson is a path from open visibility toward hidden exchange. Light crosses the room and carries electromagnetism in a form that can be seen. Gluons bind quarks in a world that cannot be entered directly. The W boson appears at an even narrower doorway, where the identity of matter can change while the outer world remains calm. A stone on a path, a glass of water, a body resting in a quiet room, all seem unchanged from moment to moment. Beneath them, the fields remain present, and the carriers of force keep the small rules by which matter holds together, moves, shines, and sometimes becomes something else. The photon and the W boson both belong to the same broad family of force carriers. Yet they move through the story of nature with almost opposite fates. One is light without rest, crossing space with a patience that can outlast stars. The other is heavy, charged, and brief, appearing only in the narrow places where matter changes its internal name. Both are quanta of fields. Their difference shows how mass shapes the behavior of a force. A photon begins wherever energy is released in the electromagnetic field. It may come from an electron changing its arrangement around an atom, from the hot surface of a star, or from the early universe itself. Once free, it travels as a small packet of electromagnetic disturbance. It carries energy and momentum. It may be red, blue, infrared, ultraviolet, or stretched so long that its wavelength can pass over hills and cities. Still, underneath those different forms, it remains a photon. Because the photon has no rest mass, there is no internal decay waiting for it. It has no lighter pair of particles into which it can quietly fall while still obeying the conservation rules that govern energy, momentum, charge, and spin. It can be absorbed by matter. It can scatter from dust. It can lose energy as space itself expands, shifting toward longer wavelengths. But it does not simply come undone in the emptiness between galaxies. In that sense, a photon can be a very old traveler. Some photons have been moving since the first atoms formed, and light began to travel freely through space. Cosmic expansion has stretched their energy until they arrive as a cold microwave glow, surrounding the sky from every direction. Such light carries the memory of an earlier, hotter universe in silence. Nothing inside the photon has grown tired. The W boson cannot live that way. Its mass changes everything. A real W boson contains a large amount of energy in the form of mass, and that energy is not locked away without exit. Many lighter particles are available as possible decay products. A W- can pass into an electron and an electron antineutrino, or into a muon and its antineutrino, or into a tau and its antineutrino. It can also decay into quark combinations when the conservation rules allow it. Each permitted path is an opening through which the W boson can spend its energy. Its lifetime is therefore almost beyond ordinary comparison. It does not move through space long enough to become a traveler. It is born in a high-energy collision, or appears virtually within a nuclear process, and it fades before a beam of light could cross a proton. The word before is already too slow. Human speech unfolds in seconds, breath in seconds, thought in fractions of seconds. The W boson belongs to a measure of time so small that it is known through equations and traces, not through any direct act of watching. This short life gives the weak interaction its small range. A force carrier with no mass can give its force an unlimited reach. A carrier with large mass makes the interaction shrink close to the event. The field can still exist everywhere, but the exchange that produces a weak interaction is strongly suppressed outside a tiny distance. At the scale of a nucleus, even that tiny distance matters. At the scale of a molecule, it is already nearly gone. At the scale of a room, it leaves no ordinary pull or push to be felt. The W boson is not only heavy, it is electrically charged. There are two charged versions, the W plus and the W minus. Their charges are equal in size and opposite in sign, and this charge is part of their work. The photon carries no electric charge. It can move between charged particles without becoming charged itself, transferring energy and momentum while leaving their basic identity unchanged. The W boson carries charge directly, so a particle interacting through it often must change to keep nature's accounting balanced. A down quark has one value of electric charge. An up quark has another. When a down quark emits a W minus, the difference in charge is carried away, and the quark becomes an up quark. A particle has crossed from one flavor to another. The W boson is the allowed bridge. The same logic works in the opposite direction when an up quark becomes a down quark through a W plus. Charge conservation is not broken, it is obeyed through transformation. The photon has no such role. It can make an electron recoil. It can let two charged particles exchange momentum. It can carry light from the surface of a star to the surface of a planet. But an electron that emits or absorbs a photon remains an electron. A quark that feels the electromagnetic force through a photon remains the same flavor of quark. The photon moves and measures. The W boson permits change. The Z boson belongs beside the W boson in the weak family, but it carries no electric charge. It can let particles scatter through weak, neutral current interactions while keeping their charge and identity. A neutrino may interact through a Z boson and remain the same kind of neutrino afterward. The Z boson opens another quiet doorway into weak physics, but it does not perform the charge transformation that defines the W boson's place. This difference gives the weak interaction a strange double character. One part of it can scatter particles without changing their identity. Another part can rearrange identity itself. The W boson is the charged part, the part that lets a particle cross from one member of a family to another. This is why it appears in beta decay, in stellar fusion, in neutrino interactions, and in the early universe balance between protons and neutrons. Its work is not frequent under ordinary conditions, but when it happens, the result can shape the matter involved. There is a quieter relation behind the contrast. At very high energies, before the universe cooled into its present form, the weak force and electromagnetism were not separate in the way they appear now. They were part of one electro-weak structure. The photon and the W bosons did not yet have the same divided fates. Then the Higgs field settled into its present background value, and the pattern changed. The W and Z bosons became massive. The photon remained massless. After that change, two kinds of reach existed. Electromagnetism could stretch outward through the massless photon. The weak interaction withdrew into the inner scale of matter, carried by massive bosons that could not travel far. The split is written into every atom, into the slow decay of unstable nuclei, into the steady burning of stars, and into the fact that light can arrive from distances where no W boson could remain alive, long enough to cross the smallest fraction of the path. So the photon and the W boson stand as two quiet examples of how a field's quantum can shape a force. One is a long-lived messenger of light and charge, moving across the open dark. The other is a short-lived carrier of charge transformation, appearing in hidden places where matter changes from within. Their contrast is not only a fact about particles, it is a fact about the structure of the visible universe, where some influences can cross the sky, and others work only in the small chamber of the nucleus. The weak interaction has a name that can mislead the ear. It sounds small in the ordinary way, as though it barely matters. as though it belongs near the edge of the physical world rather than close to its center. Yet the weakness is not a measure of importance. It is a measure of reach. The weak force changes matter, opens paths for radioactive decay, helps stars begin their long burning, and connects neutrinos to the rest of the material universe. Its work is quiet because its range is narrow. That narrowness comes from the mass of its carriers. A photon has no rest mass, so electromagnetism can reach outward without a fixed boundary. The W boson has a large mass, and that mass changes the shape of the force it carries. A massive carrier cannot produce the same long, gentle field that a massless carrier can. Its influence fades much faster, not merely by spreading thinner, but by being cut off at subatomic distance. The weak interaction becomes a contact-like event, confined to spaces far smaller than the atom that contains it. The scale is difficult to hold in thought. An atom may be pictured as a small cloud, with electrons occupying a wide region around a compact nucleus. The nucleus itself is tiny compared with the atom, as though a seed were suspended inside a room. The weak interaction works across distances smaller still. Even the nucleus becomes a wide country beside the tiny range through which a W boson can effectively carry its force. Ordinary space has no room for this interaction to announce itself. The reason is not that the weak field is absent outside the nucleus. Fields are not small objects placed in one location. They extend through space according to their own rules. The weakness arises because the exchange of a heavy carrier is strongly suppressed at distances larger than the allowed span. A W boson, real or virtual, is too costly an energy to act like a long-range messenger. The field may be there, but the kind of exchange that changes particles can only occur when the participants are extremely close. In nuclear processes, the W boson usually appears as a virtual carrier. The word virtual can sound unreal, but that is not the right feeling for it. A virtual particle is not a fake particle added for convenience. It is an intermediate part of the quantum process, a temporary disturbance described by the same field that gives rise to real particles when enough energy is available. It cannot be caught as a free object in a detector. It does not travel away like a finished fragment from a collision. It exists within the interaction itself, between the beginning and the end. In ordinary beta decay, there is not enough energy to create a real W boson. A neutron changing into a proton releases only a small amount of energy compared with the mass energy of the W boson. The difference is enormous by particle standards. A full W boson is far too heavy to be produced honestly in that quiet nuclear change. Yet the process can still occur through a virtual W boson because quantum mechanics allows a temporary intermediate state to contribute as long as it remains confined to an extremely short interval. The shorter the interval, the larger the temporary energy mismatch that can be involved. This is one way the energy-time uncertainty relation enters the story. It does not permit ordinary chaos, and it does not allow energy conservation to be ignored in the finished event. The beginning and the end still balance, but in the middle of a quantum process, for a time too small to separate into ordinary moments, the field can pass through an intermediate state that would be impossible as a lasting free particle. The heavy W boson therefore behaves like a messenger with almost no time to move. The larger the mass of the virtual carrier, the shorter the distance over which the interaction can take place. This is why the weak force reaches only across a fraction of a proton's width. The carrier's mass pulls the interaction inward, binding it to the tightest regions of matter. It is not held in by a wall. The limit comes from the mathematics of the field and the energy required for the exchange. This creates a special kind of hiddenness. Electromagnetism writes itself across the world in visible light, in sparks, in color, in the resistance of solid matter. Gravity writes itself into falling bodies, tides, moons, and the slow turning of galaxies. The strong force is hidden inside nuclei, but its strength is felt in the mass and stability of atomic cores. The weak interaction is quieter still. It appears when a nucleus changes its composition, when a neutrino at last touches matter, when a star slowly makes the first difficult step from hydrogen toward helium. The interaction is rare under ordinary conditions because the heavy W boson makes the process difficult. A proton inside the Sun may collide again and again in the hot plasma of the core, sharing energy with other protons for ages before the weak interaction changes one of its quarks. Most encounters do not pass through that narrow doorway. They scatter and move on. The slow pace is not an accident at the edge of the theory. It is part of the way the W boson's mass controls the rhythm of stars. If the W boson were lighter, the weak interaction would reach farther and act more readily. Radioactive decays would change their pace. Nuclear reactions in stars would proceed differently. The balance between proton and neutron in the early universe would settle into another pattern. The first light elements would form in different amounts. The quiet periodic table familiar to chemistry would not have the same arrangement of stability and decay. If the W boson had no mass at all, the contrast with the photon would disappear in a deeper way. The weak force would not remain confined to the nucleus. It would become long-range, reaching outward through space, with a carrier able to travel freely. Electromagnetism and the weak interaction would no longer appear as separate forces in the familiar low-energy world. That was once closer to the condition of the young universe, before the Higgs field settled into the pattern that gives the W and Z bosons their mass while leaving the photon massless. The present universe is already shaped by that separation. Light can cross the dark between galaxies because the photon remains massless. Weak transformation stays inside the small interiors of particles and nuclei because the W boson is heavy. One carrier opens a long road through space. The other opens a narrow door through identity. Both are needed for the familiar world, but they work in different silences. The weak force therefore lives at a strange boundary between absence and consequence. It is nearly invisible in ordinary experience. It cannot be felt as a pull through the hand or seen as a glow in the air. Its range is too short, its carrier too heavy, its events too small and too brief. Yet in those small events, it changes the internal structure of matter. It lets unstable nuclei move toward other forms. It gives neutrinos their faint connection to atoms. It slows the burning of stars into a long, measured release of light. The force called weak is not weak because it is minor. It is weak because it is close, because it works only where particles almost meet, because its messenger is born heavy and cannot carry the message far. In that nearness, the universe finds one of its deepest forms of change. The W boson does not cross the sky. It does not linger in open space. It appears in the smallest rooms of matter, and there, for less than the smallest imaginable breath, it allows one thing to become another. Long before the W boson could be named in the language of detectors, it existed as a requirement inside the equations. The weak interaction had already left its quiet traces in radioactive decay, in neutrinos slipping through matter, and in the slow nuclear changes that keep stars alive. Physicists could see the footprints of something carrying charge and allowing particles to change identity, but the carrier itself remained beyond reach. It was too heavy to appear in ordinary nuclear decay, too short-lived to be watched directly, and too brief to leave a track like an ordinary charged particle moving through a chamber. The search for it moved into the world of large machines. At CERN, beneath the fields and roads near Geneva, particle beams were shaped, cooled, accelerated, and guided through circular tunnels. The instruments did not resemble a simple microscope pointed at a tiny object. They were closer to artificial storms built with great care, places where matter could be given enough energy to make short-lived particles rise from the fields that fill space. A detector waited around the collision point, like a many-layered eye, not watching the W boson itself, but watching the particles that would appear after it vanished. The machine at the center of the discovery was the superproton synchrotron, changed into a collider where protons and antiprotons could meet head-on. Protons are familiar members of atomic nuclei. Antiprotons are their antimatter partners, with the same mass and opposite charge. Bringing them together at very high energy allowed the energy of motion to become the mass of new particles. In those collisions, the quantum fields could be disturbed strongly enough to produce W and Z bosons as real particles, not merely virtual carriers inside a quiet decay. The preparation was delicate. Antiprotons are not waiting in ordinary matter. They must be made, gathered, slowed, and focused, and they disappear when they meet ordinary protons outside the intended collision. The technique of stochastic cooling, developed by Simon van der Meer, made it possible to collect and refine antiproton beams with enough precision for the experiment to work. It was a patient act of control over particles that did not want to remain gathered. The beam had to become narrow, ordered, and bright enough for rare events to appear from the background. The UA-1 detector, led by Carlo Rubbia and a large collaboration, stood around the collision region to catch the results. It did not wait for a W boson to draw a line across its layers. The W boson would not survive long enough. Instead, the detector searched for a particular absence and a particular presence together. One possible W decay produces a charged lepton, such as an electron, and a neutrino. The electron can leave energy in the detector. The neutrino usually escapes, carrying momentum away without leaving an ordinary mark. The event is seen partly through what appears and partly through what is missing. That missing momentum was not emptiness. It was evidence of a particle that had passed through unseen. In a carefully balanced collision, the outgoing particles should carry momentum in a way that accounts for the whole event. When a high-energy electron appears on one side and the rest of the visible debris does not balance it, the detector records a silent imbalance. The neutrino has taken the unseen share. Together, the visible lepton and the missing momentum form the signature of a W boson that existed only for a tiny fraction of time before decaying. In 1983, the first clear events appeared. They did not look like a portrait of a particle. They looked like patterns in the detector, energy deposits, tracks, missing transverse momentum, and statistical separation from more ordinary collisions. The announcement did not make the W boson less brief. It made the theory visible through its consequences. The carrier predicted by electroweak theory had stepped into the measurable world for just long enough to leave a trace after its disappearance. The Z boson followed in the same season of discovery, leaving a cleaner kind of signal in some events because it could decay into pairs of charged leptons. Together, the W and Z bosons completed a central part of the electroweak picture. The weak force and electromagnetism, different in the low-energy world of atoms and human experience, could be understood as related parts of a deeper structure. The photon remained massless. The W and Z bosons were heavy. The broken symmetry that separated the forces had left measurable particles behind. The discovery brought the Nobel Prize in Physics to Carlo Rubbia and Simon van der Meer in 1984. The prize recognized not a single isolated moment, but the union of theory, engineering, beam control, detector design, and patient analysis. A particle that could not be watched directly had been found through the disciplined reading of its decay. The event showed how modern physics often approaches the hidden world. It does not always see the object itself. It reconstructs the object from the arrangement of what remains. There is a quiet beauty in that method. A W boson is born in a collision with enough energy to make its mass real. It lasts for less than a time that ordinary thought can divide. Then it decays into particles that move outward into the detector. By the time the instruments register the aftermath, the W boson is already gone. Yet its mass, charge, and lifetime are written into the pattern. The detector reads the grammar left behind by an event that no human eye could ever witness. Over the years that followed, more measurements refined the picture. The mass of the W boson became one of the carefully measured numbers in particle physics. Its decay patterns were counted. Its relationship to the Z boson, the photon, the top quark, and the Higgs field became part of the network of tests that hold the Standard Model together. Each new measurement pressed gently on the theory, checking whether the values agreed with the structure that had predicted them. The W boson's discovery also changed the feeling of the weak interaction. Before, the force had already been known by its effects. Beta decay had been measured, neutrinos had been inferred, and then detected. The mathematical theory had joined the weak and electromagnetic forces in a single electroweak framework. But a theory of force carriers asks for carriers. The W boson's appearance in collider data gave the weak interaction a direct body within the standard model. Even if that body lived for less than a moment, the machines have grown since then. Later, colliders produced W bosons in much larger numbers, allowing their properties to be measured with greater care. The Large Hadron Collider continues that work at higher energies, surrounded by detectors vast enough to wrap a building around a collision point, yet tuned to catch events smaller than a nucleus. The W boson remains too brief to see directly. It is still known by decay products, by missing momentum, by distributions, by repeated patterns in many collisions gathered over years. This is the calm paradox of the discovery. The W boson is real, but not in the way a grain of dust is real. It cannot be placed under a lens or held after the event. It is real as a quantum of a field, as a carrier whose mass and charge can be measured, as a fleeting participant whose absence leaves a reliable shape in the data. The machines at CERN did not make the W boson a permanent object. They made the conditions in which its brief life could be written clearly enough to read. From that point onward, the weak interaction was no longer only a hidden transformation inside nuclei. It had a measured messenger. Heavy, charged, short-lived, and central to the changing identity of matter, the W boson had crossed from prediction into evidence, appearing in the controlled fire of a collider and vanishing into the particles that proved it had been there. A proton and a neutron look almost like neighboring stones in the same small wall. They sit together in the nucleus, pressed close by the strong force, carrying most of the mass of the atom. To chemistry, their difference is decisive. A proton carries positive electric charge and helps name the element. A neutron carries no electric charge and changes the weight and stability of the nucleus. Yet beneath that difference, they are built from nearly the same ingredients. A proton contains 2 up quarks and 1 down quark. A neutron contains 1 up quark and 2 down quarks. The shift from one particle to the other is not a large rebuilding. It is the change of 1 quark. 1 down quark becomes an up quark, and the neutron becomes a proton. 1 up quark becomes a down quark, and the proton becomes a neutron. Matter changes its name by changing a single hidden part of its inner pattern. This is where the W boson does what no photon can do. The photon may carry electromagnetic force between charged particles, but it leaves their identities intact. An electron remains an electron after exchanging a photon. A quark remains the same flavor after feeling electromagnetism. The strong force binds quarks tightly inside protons and neutrons, but it does not turn one flavor into another. The W boson belongs to a narrower and stranger action. It opens the allowed path by which a quark crosses from one flavor to another. Flavor is the name physicists give to the type of a quark or lepton. The word sounds almost gentle, borrowed from ordinary life, but it marks a real property of elementary particles. Up, down, strange, charm, bottom, and top are quark flavors. Electron, muon, tau, and their neutrinos form related families among leptons. The weak interaction is the part of nature that can move particles between these identities, under strict rules of charge, energy, and probability. In the most familiar nuclear change, a down quark becomes an up quark. A down quark has electric charge equal to -1/3 of the proton's charge. An up quark has positive 2/3. The difference between them is 1 full unit of positive charge. If the down quark is to become an up quark, the missing balance must go somewhere. The W- boson carries away 1 unit of negative charge, and the accounting is kept exact. The quark changes, the charge is conserved, and the neutron that held the quark becomes a proton. The W boson's charge is therefore not a small detail attached to its name. It is the reason the transformation can happen. A neutral carrier could not do this same work in the same way. The Z boson, which is also part of the weak interaction, can allow particles to scatter without changing electric charge. The W plus and W minus are different because their own charges force the particles around them to change accordingly. They do not merely pass motion through matter. They carry the charge that makes a new identity possible. Inside a neutron, the change is hidden within a dense moving system. Quarks are not little beads sitting still in a tidy triangle. They are bound by gluons, surrounded by fields, confined within a particle whose interior is restless, even when the neutron itself seems steady. The language of three quarks gives the right identity, but the full interior is a sea of strong force activity. In that confined motion, a weak interaction can occur. One down quark emits a virtual W minus and becomes an up quark. The larger particle changes with it. The neutron has become a proton. The virtual W minus does not last as a free object. In ordinary beta decay, there is not enough energy to create a real W boson with its full mass. The W exists as an intermediate state within the process, an extremely short bridge between the old arrangement and the new one. It then gives rise to an electron and an electron antineutrino. The electron carries negative charge outward. The antineutrino carries away energy and momentum with almost no contact with the surrounding matter. From outside the nucleus, the whole change may appear as radioactive decay. A nucleus has shifted. Its number of protons has increased by 1. A chemical element has become the next element in line. Carbon-14 becomes nitrogen-14 in this way. Tritium becomes helium-3. Potassium-40 can become calcium-40 by a related weak process. These examples are familiar in geology, biology, medicine, and the quiet background of natural radioactivity, but the central act is always subnuclear. A quark changes flavor through the weak interaction. The opposite movement can also occur. In a proton-rich nucleus, an up quark can become a down quark through the action of a W plus boson. The proton becomes a neutron. The W plus gives rise to a positron and an electron neutrino. This is beta plus decay, and it appears in certain unstable nuclei. The positron does not usually travel far before it meets an electron. Matter and antimatter then annihilate into photons, often gamma rays, which can be detected in medical imaging. A hospital scan can therefore depend, quietly and practically, on the same weak process that changes quark flavor inside a nucleus. The scale of the event remains very small, but the bridge to daily life is real. A patient lying still in a scanner is not seeing the W boson. The instruments are not catching the boson itself. They are detecting later traces, photons from positron annihilation, patterns reconstructed by computers, images built from decay events inside the body. The W boson's part has already ended long before the signal reaches the detector. Still, without that hidden charge transformation, the chain of evidence would not begin. This is the counterintuitive nature of the weak force. The word force suggests pushing, pulling, attracting, repelling. The weak interaction can do those things in its own limited ways, but its charged current reaches deeper. It changes membership. It turns one particle type into another. The action is not like moving a chair across a floor. It is closer to changing the chair's material while the room stays outwardly quiet. The analogy soon breaks, but it gives a soft outline of the difference. Identity, not only motion, is at stake. The transformation also obeys boundaries. The W boson does not allow any particle to become any other particle without pattern. Quarks change between up-type and down-type families. Up, charm, and top belong on one side. Down, strange, and bottom belong on the other. The weak interaction connects the two sides with probabilities that are not equal. Some transitions are common, others are rare. The measured pattern of these probabilities forms one of the delicate maps of particle physics, linking generations of quarks in a way that has to match experiment. For ordinary matter, the lightest quarks matter most. Up and down quarks build protons and neutrons. Their weak changes shape nuclear stability, radioactive decay, and the first steps of stellar fusion. Heavier quarks appear in high-energy events and vanish quickly through weak decays of their own. Even there, the W boson is often present as the channel of change, allowing heavy flavors to descend into lighter ones until the stable matter of the familiar world remains. The W boson therefore sits at a quiet crossing point. On one side are the identities of particles, written in flavor, charge, and family. On the other side are the large consequences that arise when those identities shift. Elements changing, neutrinos escaping, stars burning slowly, and matter settling into stable forms. The crossing is narrow. The carrier is heavy. The event is brief, yet the rule it carries is one of nature's deepest freedoms. Matter is stable enough to endure, but not so fixed that change is forbidden. Radioactive decay often enters the imagination wearing the wrong kind of light. It is pictured as a warning sign, a harsh glow, a danger sealed behind thick walls. Those images belong to certain human uses and certain dangerous materials, but they do not describe the full quietness of the process. Radioactivity also belongs to old rock, to traces of carbon in bone, to potassium in the ground, to the slow, inward histories of atoms that have been changing since before any living eye opened on Earth. Beta decay is one of the gentlest ways to hear that hidden history. A nucleus sits within an atom, holding protons and neutrons in an arrangement that may not be perfectly settled. The imbalance can be small. Too many neutrons may make the nucleus lean toward one kind of change. Too many protons may make it lean toward another. Nothing about the outer surface of the material needs to look restless. A mineral can lie cold in a cliff. A seed can sleep under soil. A fragment of charcoal can remain black and still. Inside some of its atoms, a weak process slowly changes the count of protons. When beta- decay occurs, a neutron becomes a proton. The inner cause lies in a down quark, changing into an up quark through the weak interaction. A virtual W- boson carries the charged part of that change, then gives rise to an electron and an electron antineutrino. The electron leaves the nucleus as beta radiation. The antineutrino passes outward almost without touching anything, carrying a faint share of energy and momentum into the wider dark. The nucleus has changed more than its weight. It has changed its elemental identity. An element is named by the number of protons in its nucleus. Add one proton, and the atom moves to the next place in the periodic table. Carbon-14 becomes nitrogen-14. That change is not a chemical reaction on the surface. It is not a bond forming or breaking between atoms. It is a change in the inner count, a small rearrangement of identity carried by the weak force. Carbon-14 gives this process one of its most familiar clocks. It forms in the upper atmosphere when cosmic rays strike atoms and generate neutrons that interact with nitrogen. From there, carbon-14 enters carbon dioxide, plants, animals, shells, wood, cloth, and bone, joining the ordinary exchange of carbon through living systems. While an organism lives, the carbon inside it remains tied to the atmosphere and biosphere. After death, that exchange slows and stops. The carbon-14 already present begins to decay into nitrogen-14 at a measured average pace. The clock is not mechanical. No hand turns, no gear clicks. It is statistical, made from enormous numbers of atoms, each one unpredictable in its individual moment of decay, yet steady in the average behavior of the whole group. Half-life is the name for that average rhythm. For carbon-14, after about 5,700 years, roughly half of a starting amount has changed. After another span of the same length, half of what remains has changed again. The curve descends softly, never by command of a single atom, but by the collective patience of many. In that patience, archaeology finds time. A piece of charcoal from an old hearth, a fiber from a woven cloth, a seed from a buried layer, or a bone fragment from an ancient animal can still hold a measurable trace of carbon-14. The remaining amount does not speak in words. It gives a ratio. From that ratio, with calibration and care, a date can be estimated. The W boson does not appear in the report that names the age of the sample. Its role is far too small and too brief for such a line. Yet the dating method depends on the same weak transformation repeated across countless atoms. Other beta decays keep different clocks in stone. Potassium-40, present in many minerals and in small amounts in living tissue, can change through weak processes into argon-40 or calcium-40. In volcanic rocks, argon can become trapped after cooling, allowing geologists to estimate when the rock last hardened from molten material. The method opens long stretches of Earth history, reaching far beyond the range of carbon dating. In old lava, ash layers, and mineral crystals, beta decay helps turn silent stone into a record of time. Tritium, a heavy form of hydrogen, carries another example. Its nucleus holds one proton and two neutrons. Through beta decay, one neutron becomes a proton, and tritium becomes helium-3. This process matters in studies of water movement, nuclear science, and the upper atmosphere. The atom is light. The change is small. Still, the same principle remains. A neutron changes into a proton because the weak interaction allows one quark to change flavor. Beta plus decay moves in the other direction. In some proton-rich nuclei, a proton becomes a neutron, an up quark becomes a down quark, and a W plus boson carries the required charge through the process. The W plus gives rise to a positron and an electron neutrino. The positron is the antimatter partner of the electron. It does not usually remain long in ordinary matter. After losing some energy, it meets an electron, and the two annihilate into photons. That quiet annihilation is the basis of positron emission tomography. A tracer containing a positron-emitting isotope is placed into the body, often attached to a molecule involved in metabolism. The isotope decays. The positron travels a short distance and meets an electron. Two gamma-ray photons fly away in nearly opposite directions. Detectors around the body catch them, and a computer reconstructs where the decay likely occurred. A medical image emerges from many small, weak decays, each beginning with a W boson's brief charged work inside a nucleus. This does not make the body strange. It shows that the body already belongs to the same physics as stars, stones, and early matter. The weak interaction is not limited to distant machines or rare laboratory events. It is part of the ordinary inventory of nature, appearing wherever the right unstable nucleus exists. Most atoms in ordinary matter are stable on timescales so long that no change matters to daily life. A few are not. They carry hidden clocks. The danger of radioactivity depends on the isotope, the type of radiation, the amount, the energy, and the way it enters or approaches living tissue. The underlying act, however, is not angry or purposeful. A nucleus has an allowed path toward a lower or more stable arrangement, and the weak interaction opens that path. The W boson carries the charge change at the smallest level. The electron, positron, neutrino, or antineutrino carries the result outward. Matter steps from one identity into another. Seen this way, beta decay is less a violent break than a slow grammar of transformation. It writes time into carbon, heat into some rocks, signals into detectors, and faint neutrinos into space. It changes elements without flame. It moves through matter without needing any visible wound. In its smallest moment, a quark changes flavor. In its larger consequence, an atom changes name. A buried fragment becomes datable. A stone remembers cooling. A scan becomes an image. The W boson is gone before any of these meanings appear, but the path it opened remains. Among the particles that pass through the universe, the neutrino is one of the least willing to leave a mark. It moves through rock, water, metal, flesh, and the wide dust between stars with almost no disturbance. A stream of solar neutrinos passes through Earth every moment, entering one side of the planet and leaving the other as though the whole world were only a thin mist. Most never strike a single atom. Most keep going. This near invisibility is not emptiness. A neutrino carries energy. It carries momentum. It has a tiny mass, smaller than any charged particle known, though not zero. It comes in different types associated with the electron, the muon, and the tau. It is real enough to be counted in careful experiments, real enough to carry messages from the sun, from exploding stars, from nuclear reactors, and from the earliest times after the Big Bang. Yet it is almost cut off from ordinary matter. The reason lies in the forces it can feel. A neutrino has no electric charge, so the photon does not connect it to the electromagnetic field. It does not carry color charge, so gluons do not bind it into the strong force world of quarks. Gravity acts on it, as gravity acts on all energy and mass. But the effect is faint for a particle so light. The main doorway between a neutrino and the material world is the weak interaction. That doorway is opened by the W and Z bosons. The W boson gives one kind of connection. It can turn a neutrino into its charged partner, or a charged lepton into its neutrino, while carrying the needed electric charge through the interaction. An electron neutrino can interact with matter by exchanging a W boson and producing an electron. A muon neutrino can produce a muon. A tau neutrino can produce a tau, if enough energy is available. The Z boson gives another kind of connection, a neutral current interaction in which the neutrino scatters and remains a neutrino afterward. Together, these weak carriers form the small gate through which neutrinos touch matter at all. The gate is narrow because the W and Z bosons are heavy. The same heaviness that confines beta decay to the inner scale of nuclei also makes neutrino interactions rare. A photon can be exchanged readily between charged particles across large distances. A W or Z boson is costly. Its exchange can happen only when the conditions line up at extremely short range, with the right energy and quantum properties. The neutrino therefore crosses almost everything before the weak force offers a chance to interact. This made the neutrino seem almost like a ghost when it first entered physics. In beta decay, electrons emerged from nuclei with a spread of energies that did not fit a simple two-particle decay. Energy and momentum appeared to be missing. In 1930, Wolfgang Pauli proposed that an unseen neutral particle carried away the missing share. The proposal saved conservation laws, but it asked nature to contain a particle so hard to detect that Pauli himself treated the idea with caution. Enrico Fermi later built the theory of beta decay around this little neutral particle and gave it the name neutrino. For many years, the neutrino remained a necessary absence. It made equations balance. It explained the continuous energy spectrum of beta particles. It gave beta decay a hidden partner, but detectors found nothing for a long time because the particles scarcely interacted. The first confirmed detection came in the 1950s, when Clyde Cowan and Frederick Rines used a nuclear reactor as a strong source of antineutrinos and watched for the rare cases in which one interacted with matter. A large detector, many antineutrinos, and careful patience turned absence into evidence. The reaction they used depended on the weak interaction. An electron antineutrino met a proton and produced a positron and a neutron. A W boson mediated the change at the smallest level. The positron soon annihilated with an electron, giving a pair of gamma rays. The neutron was captured later, giving another signal. The timing of those signals marked the passage of an antineutrino that had finally touched matter. Once again, the W boson itself was not seen directly. Its presence was read through the permitted change. Since then, neutrino detectors have become quiet cathedrals of patience. Some are buried deep underground, shielded from ordinary cosmic rays by rock. Some hold immense volumes of water, heavy water, ice, or liquid scintillator. They wait for tiny flashes of light, brief cones of blue Cherenkov radiation, or other signs that a neutrino has interacted with an atom inside the detector. The vast majority pass through without contact. The rare few that stop, scatter, or transform carry information from places light cannot escape. Neutrinos from the Sun are born in nuclear reactions in the core, including weak processes tied to the first step of hydrogen fusion. Photons from that core take a long wandering path outward, scattering again and again before reaching the surface. Neutrinos leave almost immediately. They pass through the solar material as if the star were transparent, carrying news from the deep center to space. Detectors on Earth catch only a tiny fraction, but enough to confirm that the Sun is making energy through the nuclear reactions theory describes. For a time, fewer solar neutrinos were detected than expected. The missing number became known as the solar neutrino problem. The answer did not come from a broken sun, but from neutrinos changing type as they traveled. Electron neutrinos born in the solar core could become muon or tau neutrinos before reaching Earth. This process, called neutrino oscillation, showed that neutrinos have mass. It opened another soft fracture in the older picture, because the simplest early form of the Standard Model had treated neutrinos as massless. The weak interaction revealed them, but their masses pointed towards something still unfinished. The W boson is therefore part of a story that reaches beyond a single particle. It is the charged gatekeeper between neutrinos and charged matter. It appears in beta decay, in reactor detection, in stellar fusion, and in high-energy collisions where neutrinos emerge with other particles. It allows a neutrino to become visible only by making something else visible: an electron track, a positron flash, a missing balance in a detector, a faint light in deep water or ice. There is a calm humility in neutrino physics. The universe is full of particles moving through matter without resistance, and ordinary matter is full of space through which they pass. A human body, a mountain, and a planet are almost transparent to them, yet the weak interaction keeps them from being completely disconnected. The gate rarely opens, but it opens. Through the W and Z bosons, the ghost-like particle touches the atom, and the atom answers with a trace of light, charge, or motion. The weak force is narrow, and because it is narrow, neutrinos travel almost freely from hidden places. They come from the Sun's core, from reactors, from particle accelerators, from radioactive decays, and from stellar explosions whose interiors would otherwise remain sealed. The same heaviness that makes the W boson brief gives neutrinos their long reach through matter. A short-lived carrier creates a universe where some messengers pass through almost everything, holding in their faint motion the memory of events buried deep inside stars. A mirror seems to promise fairness. A hand lifted on one side appears as a hand lifted on the other. A spiral shell, a turning wheel, a body moving through a room, all can be reflected into a reversed version that still feels possible. For a long time, it seemed natural to imagine that the deepest laws of physics would keep the same promise. If a process could happen in the world, its mirror image should be allowed to happen with the same ease. Most familiar forces behave that way. Electromagnetism does not prefer left over right. A charge moving in a mirrored arrangement follows mirrored rules. The strong force also respects this kind of left-right reflection. Gravity, in ordinary settings, does not choose one-handedness of motion over the other. The world may contain left spirals and right spirals, left hands and right hands, but the underlying laws were once expected to treat the two sides evenly. The weak interaction breaks that expectation. The difference appears in a property called handedness, closely related to the way a particle's spin is aligned with its direction of motion. Spin is not a small sphere turning like a bead on a string. It is an intrinsic quantum property, a built-in angular momentum that particles carry. Yet the image of direction still helps. A particle moving through space can have its spin oriented in one relation to its motion, or the opposite relation. At very high speeds, this relation becomes a meaningful way to describe whether the particle behaves as left-handed or right-handed in weak interactions. For photons, gluons, and many familiar interactions, this distinction does not decide whether the force can act. But the W boson is selective. It couples to left-handed particles and right-handed antiparticles. A left-handed electron can take part in charged weak interactions. A right-handed electron does not couple to the W boson in the same way. The field is present, the particle exists, but the charged weak door does not open for the wrong-handedness. This is not a matter of shape in ordinary space. An electron has no little left side or right side like a glove. The handedness belongs to its quantum state, to the relation between spin and motion, and to the structure of the weak interaction itself. Still, the effect is as real as any measured property in physics. The W boson does not treat the mirror image as identical. The discovery of this asymmetry came through a cold and careful experiment. In the 1950s, the conservation of parity, the idea that mirror-reflected processes should obey the same laws, was widely trusted. It had worked in the strong and electromagnetic interactions. The weak force was harder to test, and many assumptions had settled into place simply because no clear experiment had yet forced them aside. Sung-Dao Lee and Chen-Ning Yang examined the evidence and noticed the gap. The weak interaction had not been tested with enough care for parity conservation. The missing test mattered. A law that has not been checked in one part of nature may still fail there. Their proposal opened the way for an experiment by Qian-Xiong Wu and her collaborators, using cobalt-60 nuclei cooled to temperatures near absolute zero and placed in a magnetic field. The cold mattered because heat makes nuclei jostle in random orientations. To see a left-right preference, the spins of many nuclei had to be aligned, like tiny compass needles brought into order. The magnetic field gave the nuclei a common direction. The low temperature helped keep that order from being washed away by thermal motion. In that quiet, cold arrangement, cobalt-60 nuclei underwent beta decay, releasing electrons through the weak interaction. If parity were conserved, the electrons should have emerged equally along both directions of the nuclear spin axis. A mirror-reflected version of the decay would have looked just as likely as the original. The detector would have seen no preference, no leaning of nature toward one side. But the electrons did not emerge evenly. They preferred one direction relative to the nuclear spin. The mirror version was not equivalent. The results showed that the weak interaction violates parity. Nature, at this level, distinguishes left from right. The scene can be imagined without harshness. A laboratory, cooled close to absolute stillness. Nuclei aligned in a field. Electrons leaving in a pattern that refuses the old symmetry. No large object changes shape. No mirror cracks. Yet a deep assumption about physical law gives way. The weak force has a handedness built into it, and the W boson carries that preference in its charged interactions. This asymmetry is one of the most delicate facts in the Standard Model. It means that the universe is not fully symmetric under reflection. A mirror image of a weak process may not be a process that nature performs with the same probability. Left and right are not always interchangeable words. At the level where W bosons couple to fermions, one side is allowed, and the other is withheld. The effect reaches neutrinos with special clarity. In ordinary weak interactions, neutrinos are observed as left-handed, while antineutrinos are right-handed. This feature once seemed almost absolute, especially when neutrinos were thought to have no mass. The later discovery that neutrinos do have tiny masses complicated the picture, but the weak interaction still couples to them in its chiral, one-sided way. The W boson remains the carrier of this left-handed structure. There is a link here to the broader imbalance between matter and antimatter, though the full story remains unfinished. The weak interaction is one of the places where nature allows certain symmetries to be broken. Parity is broken. Combined charge parity symmetry is also broken in some weak processes involving quarks, though not strongly enough within the known Standard Model to explain the entire matter-filled universe. The W boson stands close to that unfinished question, not as a final answer, but as part of the known machinery by which symmetry can fail gently and measurably. The word failure does not carry blame here. Symmetry breaking is not disorder in a careless sense. It is a pattern that chooses one allowed form over another, a rule that permits difference where sameness was expected. In the Higgs field, symmetry breaking gives mass to the W and Z bosons while leaving the photon massless. In weak interactions, parity violation gives the W boson a preference for one-handedness of matter. These are different kinds of asymmetry, but both show that the familiar world is shaped by distinctions hidden beneath its calm surface. A mirror still reflects the room. It turns a cup handle from one side to the other. It reverses writing. It gives a face its softened double. For ordinary light, the mirror works because photons obey electromagnetic laws that respect reflection. But far below the level of glass and image, the weak interaction does not keep the same bargain. The W boson carries a force that knows handedness. It acts through one chiral side of matter, and not through the other in the same way. This makes the weak interaction feel less like a simple push and more like a rule with a direction. It changes quark flavor. It opens beta decay. It connects neutrinos to matter. It also gives the universe a left-right grain at the smallest scale, a hidden texture not visible in stones, bodies, or stars, but present in the decays that slowly change nuclei and in the particles that pass through deep detectors. The W boson is brief, heavy, and narrow in range, yet it carries an asymmetry that reaches into the form of physical law itself. The sun seems steady because its violence is deeply restrained. From far away, it gives light with a calm that feels almost constant. Dawn follows night. Warmth gathers on stone. Leaves turn their faces toward the sky, and the star at the center of the solar system appears to burn with a patience older than mountains. Inside its core, however, matter is pressed into a hot, dense plasma, and protons move through one another's electric resistance with energies that only a star can sustain. The core is not a flame in the ordinary sense. No oxygen feeds it. No wood blackens. The sun shines because atomic nuclei fuse, and because a little mass becomes energy when lighter nuclei join into heavier ones. The main path in a star like the sun is called the proton-proton chain. It begins with the simplest nucleus, the proton, which is also the nucleus of ordinary hydrogen. Hydrogen fills most of the sun, and deep in the core, those protons move fast enough and close enough for nuclear reactions to become possible. Yet the first step is not easy. Two protons can approach one another only by pushing through their mutual electric repulsion. Both are positively charged, and electromagnetism tries to keep them apart. The hot plasma gives them speed. Quantum tunneling gives some of them a chance to pass through the barrier that would otherwise stop them. Even when two protons come close enough for the strong force to bind them, one of the protons must change into a neutron for the new nucleus to hold together as deuterium. That change belongs to the weak interaction. A proton contains two up quarks and one down quark. A neutron contains one up quark and two down quarks. For one proton to become a neutron, one of its up quarks must become a down quark. A W+ boson carries the positive charge away from that transformation. The W+ then gives rise to a positron and an electron neutrino. The positron later meets an electron and annihilates, while the neutrino leaves the core almost as soon as it is born. The new neutron binds with the remaining proton, and deuterium appears. This single weak step is the narrow gate through which solar fusion must pass. It is so unlikely for any one pair of protons that a proton in the sun's core may wait for billions of years before taking part in a successful transformation. Most close encounters do not become deuterium. The protons approach, scatter, and move on through the crowded heat. Again and again, the reaction fails. The core is full of near beginnings. The slowness is not a flaw in the star. It is the reason the star lasts. If the first step of fusion were governed only by the strong force once protons came close enough, the sun would burn through its fuel far more quickly. Instead, the weak interaction places a quiet delay at the entrance. The W boson's heavy mass makes the necessary transformation rare. The sun contains an immense number of protons, so rare events still happen in great abundance across the whole core. Yet for each individual proton, the path is slow. The star shines not because the weak force is eager, but because it is reluctant in just the right way. After deuterium forms, the rest of the chain moves more easily. A deuterium nucleus can fuse with another proton to make helium-3, releasing a gamma ray. Two helium-3 nuclei can then meet and form helium-4, leaving two protons free to return to the plasma. The full result is that four protons become one helium-4 nucleus, along with positrons, neutrinos, and energy. Some of that energy begins as gamma radiation deep in the core, then moves outward through the sun by a long path of absorption and re-emission. A photon born in the core does not fly straight to the surface. The solar interior is too dense. The photon is absorbed, scattered, recreated, and redirected many times, turning a short outward distance into a long wandering history. It may take vast spans of time for the energy to reach the visible surface. When it finally escapes into space as sunlight, it can cross the distance to Earth in minutes. The light that warms a face in the afternoon has passed through a slow interior journey before entering open space. The neutrino takes a different path. Born in the weak step that makes deuterium, it hardly notices the sun around it. The plasma that traps photons is nearly transparent to neutrinos. They stream from the core almost directly, carrying information about the fusion reactions still happening inside. Solar neutrino detectors on Earth therefore listen to the sun's center in a way light cannot. The W boson opens the first gate of fusion, and one of the particles born from that gate becomes a messenger from the core. This gives the W boson a role far larger than its brief life suggests. It does not sit in the sun as a lasting ingredient. It does not travel from the core to the surface. It appears only as the charged carrier in a weak transformation, then vanishes into lighter particles. Still, every deuterium nucleus in the main proton-proton chain begins with such a change. Every long sequence toward helium depends on that first rare permission for one proton to become a neutron. The balance is delicate, but not fragile in an ordinary sense. The sun is stable because gravity and pressure hold a measured opposition. Gravity pulls the star inward. Fusion energy supports it from within. If the core cools slightly, pressure drops and gravity compresses the gas, raising the temperature and increasing fusion. If the core heats slightly, pressure expands the gas, cooling it and reducing the reaction rate. This slow self-regulation depends in part on the weak interactions bottleneck. Fusion cannot run away easily because the first step remains difficult. Stars of similar kind share this same quiet dependence. Across the galaxy, main sequence stars burn hydrogen into helium through nuclear chains shaped by weak interactions. Some stars use related cycles involving carbon, nitrogen, and oxygen as catalysts, especially at higher masses and hotter cores. Even there, weak processes appear in the larger pattern of stellar burning and element formation. The W boson is not a bright object in the sky, yet its rules help set how long many stars can remain bright. The connection reaches into ordinary life without needing to announce itself. Sunlight drives weather, warms oceans, feeds plants through photosynthesis, and supports food chains that spread through forests, fields, and seas. The energy begins in nuclear binding and mass difference, but the first successful step in the sun's main fusion path requires a W-mediated change. The leaf opening in morning light is connected, distantly and calmly, to a quark changing flavor in the deep solar core. The W boson therefore controls more than a rare subatomic event. By making the weak step slow, it gives stars time. It turns fusion from a sudden release into a long burning. It allows a star like the sun to shine over billions of years, long enough for planets to cool, oceans to gather, rocks to weather, and life to follow its own slow experiments. The boson itself is gone almost instantly, but the delay it enforces becomes the long daylight of a world. Long before stars had surfaces, before planets cooled into stone, before atoms had settled into the familiar forms that later chemistry would use, The universe was a hot sea of particles and light. Space itself was expanding, and as it expanded, the heat thinned. The earliest moments did not contain quiet emptiness. They contained fields in motion, particles appearing and vanishing, radiation pressing through everything, and interactions happening so often that matter had not yet learned how to keep a lasting shape. In that young state, the weak interaction was not a rare hidden process inside nuclei. The universe was dense and hot enough for weak reactions to happen freely. Protons and neutrons did not yet hold the fixed balance that later matter would inherit. They could change into one another through weak processes, guided by W bosons and their related carriers. A neutron could become a proton. A proton could become a neutron. Electrons, positrons, neutrinos, and antineutrinos moved through the plasma, taking part in exchanges that kept the two nuclear building blocks in a shifting conversation. The scene had no atoms yet. There were no electron clouds, no molecules, no dust, no mineral grains. Even nuclei could not remain assembled for long in the earliest heat. The energy of radiation was too great, and anything that formed could be broken apart again. Still, the future of all later matter was already being shaped. The number of protons and neutrons available would decide how much hydrogen remained, how much helium could form, and how the first chemical simplicity of the cosmos would be written. A proton is slightly lighter than a neutron. That small difference matters. In the hot early universe, when energy was abundant, weak interactions could push particles both ways. Protons could become neutrons, and neutrons could become protons, with the surrounding sea of electrons, positrons, neutrinos, and antineutrinos, helping the exchange. As the universe cooled, the heavier neutron became less favored. The balance slowly shifted toward protons. Not suddenly, not by a single event. The ratio changed as temperature fell, and as weak reactions became less able to keep pace with expansion. Expansion was the quiet clock. As space stretched, particles met less often. The universe cooled not because heat escaped into some outside region, but because the fabric of space itself grew, stretching wavelengths and lowering energies. Interactions that had once happened constantly began to fall behind. The weak processes linking protons and neutrons slowed. A moment came when they could no longer maintain full equilibrium. The balance between protons and neutrons began to freeze into place. This freeze-out was not absolute in the simple sense. Neutrons could still decay into protons, and some reactions still occurred. But the general ratio was no longer being rapidly reset by the surrounding plasma. A lasting imbalance emerged. Protons became far more common than neutrons. The exact number depended on the expansion rate, the temperature, and the strength of the weak interaction. The mass of the W boson, by setting the behavior of weak reactions, stood quietly behind that balance. The neutrons that remained were unstable when alone. A free neutron does not last indefinitely. Given time, it decays into a proton, an electron, and an antineutrino through the weak interaction. In the early universe, this meant the neutron population continued to fall during the short interval before nuclei could safely form. Each decay slightly reduced the number of neutrons available for the first nuclear building. Protons, being stable in ordinary conditions, remained. Then the universe cooled enough for deuterium to survive. Deuterium is the heavy form of hydrogen made from one proton and one neutron. Before this point, any deuterium nucleus that formed was quickly broken apart by energetic photons. The universe was filled with light hot enough to undo the small bond almost immediately. This delay is sometimes called the deuterium bottleneck, because the path toward heavier light nuclei had to wait until deuterium could remain intact. When the bottleneck opened, nuclear reactions moved quickly. Deuterium joined with protons and neutrons. Helium-3 appeared. Tritium appeared, and changed or fused onward. Helium-4 formed, containing 2 protons and 2 neutrons, a tightly bound nucleus that would become the main product of this first episode of cosmic nuclear assembly. A smaller trace of other light nuclei formed as well, including deuterium that survived, helium-3, and a little lithium. The universe did not build carbon yet. It did not build oxygen, iron, or the heavier materials that later stars would make. It built mostly hydrogen and helium, with small traces left behind like faint marks at the edge of the first fire. The amount of helium depended strongly on how many neutrons were still present. Almost every surviving neutron found its way into helium-4 because helium-4 was so stable compared with the other light combinations. Protons were plentiful, but neutrons were limited. The neutron supply, therefore, set the helium abundance. The weak interaction, by controlling the earlier proton-neutron balance and the free neutron decay, helped decide how much helium the universe carried out of its first few minutes. The result was simple and lasting. Most ordinary matter remained hydrogen. A smaller but large share became helium. By mass, helium made up roughly a quarter of the ordinary material produced in that early nuclear episode, while hydrogen made up most of the rest. This ratio is still seen across the cosmos. Ancient gas clouds, distant galaxies, and the oldest light element measurements carry the mark of those first minutes. Long before the first stars began shining, the weak interaction had already helped set the chemical starting point from which stars would later form. This gives the W boson a role in cosmic history that is easy to miss. It did not build helium directly in the way the strong force bound nucleons into nuclei. It did not make light stream freely in the way photons later would. It did not gather matter through gravity. Its work came earlier and more quietly, in the conversions that decided how many neutrons remained when nuclear building became possible. The W boson was part of the small gate through which protons and neutrons exchanged identity. That gate narrowed as the universe cooled, and the closing of the gate left a ratio behind. From that ratio came a universe rich in hydrogen. This mattered for stars. Hydrogen became the main fuel of the first stellar fires. Gravity gathered gas into clouds, clouds into dense cores, and dense cores into stars. Inside those stars, hydrogen fusion began, again requiring weak interactions in the slow first step of the proton-proton chain for stars like the Sunday. The weak force therefore shaped both the fuel supply and the later burning of that fuel. It set the early mixture, then helped control the stellar pace. Helium mattered too. The first stars formed from gas that was already carrying helium from the first nuclear minutes. Helium changed the weight, pressure, cooling behavior, and later evolution of stellar material. Over long ages, stars would turn helium into carbon and oxygen in their interiors, but the first helium did not wait for stars. It came before them, when the universe was only minutes old and still too hot for atoms. The earliest nuclei were already preparing conditions for the later history of light and matter. The weak interaction also connects to neutrinos in this early time. In the first seconds, neutrinos were not yet the almost untouching messengers they are now. The universe was dense enough that they interacted often with other particles through the weak force. As expansion continued, the rate of weak interactions fell, and neutrinos decoupled from the rest of matter and radiation. They began to travel freely, forming a background of ancient neutrinos that should still fill the universe today, colder and harder to detect than the cosmic microwave background. Those relic neutrinos are a kind of unseen afterglow from a time earlier than the first freely traveling light. Photons of the cosmic microwave background last scattered when atoms formed much later. Neutrinos slipped away far earlier, when the universe was only about a second old. Their decoupling was another consequence of weak interaction rates falling behind cosmic expansion. The heavy W and Z bosons made neutrino interactions weak at low energies. And as the universe cooled, neutrinos gradually stopped being held in thermal contact with the plasma. So the weak interaction helped create two early separations. It helped freeze the proton-neutron balance, leaving the supply of neutrons that would become helium. It also let neutrinos detach from the rest of matter, sending them into long free motion through expanding space. Both separations happened without a visible boundary. There was no wall, no surface, no edge, only rates changing with temperature, interactions becoming rarer, and the universe moving from dense unity toward the layered structure later seen in matter and radiation. The same field rules that govern beta decay in a mineral grain therefore reach back to the first minutes of cosmic time. A neutron decaying in a laboratory, a proton changing in the sun, a neutrino leaving a reactor, and the proton-neutron balance of the early universe are not separate stories in the deep sense. They are different settings for the same weak interaction. The W boson appears as the charged carrier of transformation, sometimes virtual, sometimes real in high-energy conditions, always brief, always tied to change. There is a soft symmetry in the way the smallest and largest scales meet here. A process too small to see helped determine the first composition of everything visible. The number of neutrons saved from decay became the helium fraction. The helium fraction became part of the material from which stars formed. Stars later made heavier elements, scattered them through space, and gave planets the chemistry that would follow. The path is long, but it begins with rates, masses, fields, and fleeting exchanges in a universe still bright with heat. By the time atoms finally formed much later, the early weak decisions were already fixed into the inventory of matter. Hydrogen nuclei waited to capture electrons. Helium nuclei waited as well, already carrying the two-proton, two-neutron stability set by the first nucleosynthesis. Light would eventually travel freely. Gravity would gather gas. Stars would ignite. But beneath those later scenes, the W boson had already done part of its work, allowing the young universe to choose how many protons and neutrons would move forward into time. The mass of the W boson is not only a property written beside its name, it is one of the quiet weights by which the Standard Model tests itself. A single number, measured with enough care, can press against the whole structure of particle physics. It can touch the Higgs field, the top quark, the Z boson, the photon, the weak mixing angle, and the invisible influence of particles that may be too heavy or too rare to appear directly in a detector. The number is small in ordinary units and large in the language of particles. The W boson has a mass of about 80.4 giga-electron volts. That is many times heavier than a proton, yet still far below anything that could be weighed on a human scale. Its mass is not found by placing the particle on a balance. The W boson is gone long before such an image could make sense. Its mass is reconstructed from the particles it leaves behind, from the lepton that enters the detector, from the neutrino that escapes, and from the ray that shows where the unseen particle is gone. This makes the measurement delicate. A W boson often decays into a charged lepton and a neutrino. The charged lepton can be measured with great care. Its path, energy, and momentum leave records in the detector. The neutrino is different. It passes out of the apparatus almost without contact. Its presence is inferred from imbalance, from the way the visible particles fail to account for the full motion in the event. The mass must be drawn from a shape in many events, not from one complete picture. The detectors used for such work are large, but the uncertainty they fight is extremely small. Every layer matters. The magnetic field must be understood. The lepton momentum scale must be calibrated. The response of the calorimeters must be checked. The distribution of quarks and gluons inside the colliding protons must be modeled. Background events must be separated from real W decays. Radiation from the incoming and outgoing particles must be accounted for. A tiny shift in any of these details can move the final mass by an amount that matters. This is why the W mass is a patient measurement. It is not only a matter of producing many W bosons. Modern colliders can produce them in huge numbers. The harder task is knowing the detector and the collision environment well enough that a small difference in the final curve can be trusted. The W boson dies too fast to examine directly, so the experiment must become a careful reader of aftermaths. It listens to millions of brief events and asks where the center of their combined pattern lies. The importance of the number comes from the electroweak theory. In the Standard Model, the W boson's mass is not isolated. It is related to other measured quantities through the symmetry that joins electromagnetism and the weak interaction, and through the way that symmetry is broken by the Higgs field, the mass of the Z boson, the mass of the top quark, the mass of the Higgs boson, and the strengths of the interactions all fit together in a web of constraints. Change one, and the others feel the strain. Heavy particles can also affect the W mass indirectly. Even a particle too heavy to appear in a collision can influence the theory through quantum loops, subtle corrections allowed by quantum field theory. These corrections are not visible like tracks in a detector. They are small changes in the relationships between measured values. A difference in the W mass can therefore become a soft hint of something beyond the standard model if the difference persists after every known uncertainty has been understood. Before the Higgs boson was found, precision measurements of the W boson helped narrow where the Higgs might be. The W mass, together with the top quark mass and other electroweak data, gave indirect clues about the Higgs field's particle. The theory formed a kind of closed triangle. The W boson was one side, the top quark another, and the Higgs boson the missing third. When the Higgs boson appeared at CERN in 2012, near 125 giga-electron volts, the triangle became tighter. The W mass did not become less important. It became an even sharper test. A strange chapter opened in 2022 when the CDF collaboration at Fermilab reported a very precise measurement using the full dataset from the Tevatron collider. Their value was higher than the standard model prediction and higher than many previous measurements. The difference was not a gentle statistical ripple. It was large enough to attract attention across particle physics. If such a result were confirmed by other experiments, it could mean that the known model was missing something. The result was careful, and it came from an experiment with deep experience in measuring the W boson. It could not simply be dismissed. At the same time, one measurement does not rewrite physics by itself. Precision physics is a slow conversation between experiments, theories, calibrations, and methods. A value that disagrees with expectation must be examined from many sides. Detector modeling, Parton distribution functions, recoil modeling, statistical treatment, and older combinations all become part of the question. The result sits in the data, and the field waits for other voices. Atlas at CERN later reported an updated measurement using proton-proton collision data from the Large Hadron Collider. Its value was lower than the CDF result, and in agreement with the standard model. The measurement did not erase the CDF result, but it changed the shape of the puzzle. The W boson no longer pointed in one clear direction away from the theory. Instead, the world's measurements became a set of careful stones, not all lying on the same line. Some leaned toward the standard model. One stood apart. CMS added another major piece. With a large sample of W boson decays and a detailed analysis of muons and missing momentum, the collaboration measured the W mass with high precision and found a value close to the standard model expectation. The reported mass, 80,360.2 million electron volts, with an uncertainty of 9.9 million electron volts, agreed with the standard model and with other measurements near the same region. The tension from CDF remained important, but it looked less like a doorway already open and more like a discrepancy that still needed explanation. This is how precision physics often moves. Not with a single loud turn, but with layers of checking. A detector is understood, then another. A model of the proton is refined. A background is reduced. A calibration is repeated with a known particle, often the Z boson, because its clean decays help set the scale. The W boson remains harder because the neutrino escapes, leaving an incomplete event. The missing piece must be inferred with care, and the inference depends on how well the entire collision is understood. The W mass, therefore, becomes a meeting place between measurement and theory. It is a number shaped by the Higgs field, but it is also shaped by practical knowledge of machines. It belongs to an equation, but it also belongs to magnets, silicon trackers, calorimeters, muon chambers, trigger systems, beam conditions, and years of analysis. The particle dies almost immediately, while the measurement of its mass can take a decade of human work. There is a quiet contrast in that timescale. The W boson lives for a fraction of a moment. The data it leaves may be studied for years. The event is brief, but the effort to understand it is long. A field rises, a boson appears, a lepton flies outward, a neutrino leaves through the detector unseen. Then the traces become numbers, the numbers become distributions, and the distributions become a mass with an uncertainty written beside it. The value matters because the standard model is both strong and incomplete. It has survived many tests with great precision. It describes known particles and 3 of the fundamental interactions with an accuracy that remains one of the great achievements of physics. Yet it does not explain dark matter. It does not include gravity in the same quantum structure. It does not explain why neutrinos have their tiny masses in the simple form originally assumed. It does not explain why matter dominates antimatter by the observed amount. It works beautifully where it works, and still points beyond itself. The W boson sits near that boundary. Its mass is predicted through a structure that has already passed many tests. A measured deviation could signal new particles, new interactions, or a hidden correction not yet understood. Agreement is also meaningful. Each precise agreement closes certain paths and makes other possibilities narrower. A result matching the standard model is not empty. It says that any new physics must be more subtle, more hidden, or pushed to scales that do not disturb the W mass, beyond the measured uncertainty. In this sense, the W boson is a scale for the invisible. It does not need to reveal a new particle directly. It can feel the pressure of new physics through the relationships of known fields. If unknown particles exist and couple to the electroweak sector, they may bend the expected value slightly. If no bend appears, their possible forms become more constrained. The measurement is like watching the still surface of a lake for the smallest sign of something moving underneath. Calmness can also carry information. The recent measurements leave a careful picture. The CDF result remains a significant outlier compared with the standard model and many other measurements. ATLAS and CMS have found values compatible with the standard model, with CMS reaching especially high precision at the Large Hadron Collider. The story has not become a simple victory or a simple failure. It has become a refined landscape of agreement, tension, and continued checking. The W boson remains where it has often been, at the point where confidence and uncertainty meet. For a sleep documentary, the beauty of this part of physics lies not in a sudden answer, but in the patience of the search. A particle that cannot be seen directly leaves a curve in the data. A curve becomes a mass. A mass becomes a test of the Higgs field and the standard model. Around it, entire collaborations work slowly, repeating calibrations, comparing methods, and narrowing errors until a faint difference can be trusted or allowed to fade. The W boson still does the same hidden work inside matter. It still changes quark flavor. It still opens beta decay. It still helps stars begin their long burning. Yet in laboratories, it also serves as a quiet probe of whether the known laws are complete. Its mass is not only weight. It is a message written in the electroweak structure, a small number with a long shadow, measured from particles that remain after the carrier itself has disappeared. A particle that lives for almost no time can still have a width. The word sounds as though it belongs to space, to the breadth of a river, or the distance between two walls. But in particle physics, it belongs to energy and lifetime. A sharp, perfectly stable particle would have a perfectly defined mass. Its line in an energy measurement would be narrow beyond all practical seeing. An unstable particle is different. Its mass appears with a spread, a natural broadening that comes from the shortness of its life. This broadening is called decay width. The W boson has a large decay width because it dies quickly. The two ideas are not separate. They are joined by the energy-time uncertainty relation, which links the uncertainty in energy with the time over which a state exists. A particle with a very short lifetime cannot have a mass energy known with unlimited sharpness. Its presence in data appears as a distribution, a resonance with a certain width. The wider the resonance, the shorter the life. The narrower the resonance, the longer the state can remain. A long-lived particle leaves a more precise note in the energy spectrum, like a tone that can be held steadily. A short-lived particle gives a broader note, less sharply defined, because it has no time to settle into perfect energy definition before it decays. The W boson's note is broad by the standards of elementary particles. It lasts for only about 3 times 10 to the minus 25th seconds, and its decay width records that brief existence in the language of energy. This is not only a mathematical connection, it is a way of seeing what cannot be watched. No detector follows a W boson from birth to death, as though tracking a tiny object across a screen. The W boson vanishes too quickly. Its lifetime is inferred from the statistical pattern of its decays and from the shape of the resonance it leaves in collisions. The width is one of the shadows that a short-lived particle casts into measurement. The reason the W boson has such a width lies partly in how many ways it can decay. A W- can become an electron and an electron antineutrino. It can become a muon and a muon antineutrino. It can become a tau and a tau antineutrino. These are the leptonic paths, involving particles that do not carry color charge. Each path is a possible ending, a way for the W boson's mass energy to pass into lighter particles, while charge, energy, momentum, and other quantum rules remain balanced. There are also quark paths. A W boson can decay into a quark and an antiquark of appropriate types, provided the mass and conservation rules allow the final state. Quarks carry color charge, and each quark type can appear in different color states. The colors are not visible colors, but labels for the 3 forms of strong force charge. Because of these color possibilities, quark decay paths count with extra weight. What looks like one broad family of decays becomes several allowed channels when the strong force labels are included. The W boson, therefore, has many exits. It is heavy enough to pass into several lighter combinations, and it couples strongly enough for those passages to happen rapidly. The word weak again needs care. The weak interaction appears weak at low energies because its carriers are massive and its range is tiny. At energies close to the W boson's own mass, the coupling is not feeble in the ordinary sense. The W boson decays readily because the permitted final states are open and the interaction strength is sufficient. A rough pattern emerges in the branching fractions. About 1/3 of W boson decays go into leptons and their neutrinos. About 2/3 go into quark pairs, which soon become jets of hadrons, as the strong force gathers quarks into composite particles. In a detector, the leptonic decays can appear as a clean charged lepton with missing momentum from the escaping neutrino. The hadronic decays can appear as sprays of particles, broader and more crowded, because quarks do not travel alone through open space. The detector sees not the simple ending, but the aftermath. An electron may leave a sharp deposit of energy. A muon may pass through layers with a clean track. A tau may decay again before being fully identified. Quarks become jets, spreading particles through the detector in cones of hadronic activity. Neutrinos leave almost nothing, only an imbalance in momentum that must be reconstructed from everything else. The W boson is gone at the center of these signs, but the pattern of signs is enough. The total width gathers all the allowed decays together. Each channel contributes a partial width, a share of the total probability per unit time. Add the shares, and the full decay width appears. The larger the total, the shorter the lifetime. The W boson's measured total width is a little over 2 giga-electron-volts, corresponding to its incredibly brief life. This number is not just an accounting of known decays, it is also a test of whether anything unknown might be hiding among them. If the W boson had an extra way to decay, a channel leading to particles not included in the standard model, the total width could become larger than expected. The unseen decay products might not be directly visible. They might leave missing energy, unusual event shapes, or only a slight change in the overall width. For this reason, the W boson's width is a quiet doorway into new physics. A small broadening beyond prediction could mean that the particle is spending part of its energy through an unrecognized route. This makes width measurement delicate and valuable. A mass measurement asks where the center of the W boson's resonance lies. A width measurement asks how broad the resonance is, how fast the particle decays, and whether the known exit doors account for the whole disappearance. It is a different kind of listening. The mass is the pitch of the note. The width is how quickly the note fades. At colliders, measuring the W width requires an understanding of the same difficult ingredients that shape W mass measurements. The charged lepton must be measured accurately. The missing momentum from the neutrino must be reconstructed with care. The recoil of the rest of the event, the distribution of quarks and gluons inside the proton, background processes, detector calibration, and radiation effects must all be modeled. A small change in the tail of a distribution can carry information about the width, but it can also be mimicked by imperfect knowledge of the machine or event environment. Recent measurements at the Large Hadron Collider have treated the W boson's width as a precision test in its own right. The particle is produced in enormous numbers, but abundance alone does not solve the problem. The challenge is to understand the visible and missing pieces well enough that the natural width of the W boson can be separated from all the broadening caused by detector response, collision motion, and modeling uncertainty. The work is slow, technical, and quiet, the opposite of the instant in which the particle itself disappears. There is a pleasing contrast between the W boson and the human effort used to measure it. The boson exists for less than a tiny fraction of a proton crossing time. The analysis of its width may take years. Teams refine calibrations, compare control samples, test theoretical inputs, and examine how small uncertainties move the final value. The W boson leaves no lasting object behind, but its disappearance becomes a long landscape of data. The width also reflects the structure of generations. The W boson couples to electrons, muons, and taus in nearly the same way, a principle called lepton universality. Measurements of its branching fractions test this sameness. If the W boson favored one lepton family more than expected, the pattern of decays would shift. Such a shift could point to physics beyond the standard model or to an unaccounted experimental effect. In the known measurements, the broad structure remains close to the standard model's calm expectation, though precision tests continue to search for small deviations. The quark decays carry their own information. The W boson connects up-type quarks with down-type quarks through the mixing pattern described by the quark mixing matrix. Some transitions are common, others are suppressed. In W decays, the available quark channels and their probabilities help test this pattern. The jets in a detector may look messy compared with clean leptons, but they are still governed by exact quantum rules. Inside the spray of particles is the memory of a W boson's charged coupling to quarks. A decay width, therefore, becomes more than a lifetime. It is a map of access. It says which final states are open, how strongly the W boson couples to them, and whether the total disappearance matches the expected sum. The W boson does not choose in a human sense. It follows probability amplitudes set by the fields and symmetries of the theory. Across many decays, those probabilities become branching ratios. Across many events, the invisible rules become visible statistics. The photon has no comparable width of this kind. A free photon is stable because no allowed lighter final state exists for it under the required conservation laws. Its mass is zero, its decay width is zero, and its lifetime has no internal end. The W boson stands at the other extreme among familiar force carriers. Massive, unstable, full of available paths into lighter matter. Its width is the record of that difference. Mass gives it stored energy. Couplings give it roots. The roots give it a short life. This is why the W boson can be described as a brief opening in a field rather than a persistent thing. It rises from the weak field with a defined set of possible endings already written into the rules. It can create a charged lepton and a neutrino. It can create quarks that become jets. It can mediate a transformation inside a nucleus without ever becoming a real free particle. In each setting, it is associated with passage, conversion, and disappearance. The measurement of width brings the story back to the central theme of the W boson. It is a carrier of change, and its own existence is change compressed into almost no time. It changes quark flavor. It changes nuclear identity. It helps change hydrogen into helium in stars. It helped shape the proton-neutron balance of the early universe. Then, when it appears as a real particle in a collider, it changes itself into lighter particles almost at once. Its lifetime is not separate from its nature. It is the way its nature becomes visible. In the quiet language of data, the W boson's width says that the known exits are open and that the particle uses them quickly. It also leaves a margin where new exits might someday be found, if the measured broadening ever drifts beyond the standard model with enough clarity. For now, the width remains a finely measured trace of a short-lived force carrier, a broad note from a particle that cannot hold itself in the world for long. The note fades almost instantly, but the shape of its fading can be read. The final doorway in the story is not a smaller room hidden inside the W boson. It is a change in the meaning of the word made. In ordinary matter, things are made from parts. A shell is made from calcium carbonate crystals layered by a living animal. A mountain is made from minerals, fractures, and beds of stone pressed together through time. A cell is made from molecules. A molecule is made from atoms. For much of the history of science, this pattern seemed to lead downward, each level opening into another. Because of this history, it is natural to expect the W boson to contain something smaller. Its mass is large for an elementary particle. It can decay into lighter particles. It can appear in high-energy collisions and then vanish into electrons, neutrinos, quarks, and jets. The mind is tempted to picture it as a heavy little object with internal pieces, something packed tightly enough to break apart when its brief life ends. That picture is familiar, but it is not what present evidence shows. In the standard model, the W boson is elementary. It is not made from quarks. It is not a tiny nucleus. It is not a bundle of smaller known particles held together by another force. It has no measured radius, no observed layers, no known inner structure. Within the distances tested by high-energy experiments, it behaves like a point-like quantum object, a single excitation of a field rather than a composite body. This does not mean it is simple in the ordinary sense. A field excitation is not a hard bead moving through empty space. The standard model describes the universe through fields that fill space. There is an electron field, a quark field, an electromagnetic field, gluon fields, weak fields, and the Higgs field. Particles appear as quanta of these fields, as the smallest allowed disturbances carrying specific properties. An electron is a quantum of the electron field. A photon is a quantum of the electromagnetic field. The W boson is a quantum of the charged weak fields. The field is more fundamental in this description than the particle that briefly appears. The particle is not a separate object placed into the field. It is the field in an excited state. A calm field can sit in its lowest condition. A disturbance can rise, carrying energy, momentum, spin, charge, and other quantum numbers. When that disturbance has the properties of a W plus or W minus, the measurable world calls it a W boson. This way of thinking changes the old image of matter. Empty space is not truly blank. It holds the capacity for fields to rise into particles and fall back into other states. Even in the deepest vacuum, fields remain the underlying language. The W boson belongs to that language. It is not made of a material hidden inside itself. It is made real by the excitation of a field whose rules allow charged weak interaction. Its mass, charge, spin, and couplings are not parts arranged in a tiny structure. They are properties of the field and its relationship to the other fields. The Higgs field gives an important part of that relationship. The W boson's mass does not come from internal pieces. It comes from the way the charged weak fields interact with the Higgs field after electroweak symmetry breaking. In the early, hotter universe, before the Higgs field settled into its present non-zero background value, the carriers of the electroweak interaction were massless in the symmetric description. After the Higgs field took on its present state, the W and Z bosons acquired mass, while the photon remained massless. The mass therefore comes from coupling, not composition. The W boson is heavy because it interacts strongly with the Higgs field's background. The field filling space changes the behavior of the charged weak excitation, giving it inertia and limiting the reach of the weak force. No inner machinery needs to be added. The heaviness is a relation between fields, written into the broken electroweak structure that governs the low-energy universe. This can be difficult, because ordinary language treats mass as though it always means amount of stuff. A stone has more mass than a feather because it contains more material in a denser arrangement. A proton has most of its mass, not from the bare masses of its quarks, but from the energy of the strong field binding and moving within it. The W boson's mass is different again. It is not the mass of hidden contents. It is the mass of a fundamental field excitation coupled to the Higgs field. The particle can decay without being composite. Decay is not the same as breaking into pieces that were already inside. A muon decays into an electron, a neutrino, and an antineutrino. But the electron was not waiting inside the muon like a seed inside fruit. The decay is a transformation allowed by the fields. The initial excitation disappears, and new excitations of other fields appear, carrying away the conserved energy, momentum, charge, and lepton numbers in the allowed pattern. The W boson behaves this way as well. Its decay products are created in the decay. They are not little fragments shaken loose from an interior. A W- decaying into an electron and an electron antineutrino is therefore not like a shell cracking open. It is a field process. The charged weak excitation couples to the lepton fields, and the final particles appear as allowed quanta with the right total properties. A W boson decaying into quarks works by the same deeper principle, though the quarks quickly become hadrons because the strong force does not allow them to travel freely at ordinary distances. The exit paths are not evidence of inner parts. They are evidence of couplings. Experiments have searched for signs that the W boson might be composite, or that the electroweak sector hides a deeper layer. The search is sensible. History teaches caution, because atoms, nuclei, protons, and neutrons all turned out to have structure after once seeming elementary. If a W boson had internal parts, very high-energy collisions might reveal deviations in its interactions, unusual scattering patterns, excited states, or form factors, the kinds of fingerprints that composite objects leave when probed closely. So far, the evidence agrees with the point-like, standard model picture. The answer remains honest, rather than final in a philosophical sense. Current measurements show no confirmed substructure. The standard model treats the W boson as elementary, and within tested energies the treatment works. Future physics may reveal a deeper description someday, but no confirmed result has yet shown that the W boson is composite. For the present physical world, the cleanest answer is that the W boson is not made of smaller known things. It is a quantum of the weak field. More exactly, the charged W bosons are excitations of the electroweak gauge fields after symmetry breaking has arranged them into the massive W+ and W- states. Their electric charge lets them mediate charged weak currents. Their mass comes from the Higgs field. Their short lifetime comes from their available decay channels and the strength of their couplings. Their role in matter comes from the way they connect quark and lepton families. This answer is less like opening a box and more like reaching the place where boxes stop being the right image. At the deepest tested level, nature is not built from tiny solid grains in the old mechanical sense. It is built from fields and the rules governing their excitations. Some excitations are stable enough to form lasting matter. Electrons endure. Quarks remain bound inside protons and neutrons. Photons can travel across space for great spans of time. Other excitations, like the W boson, are brief by their nature. They rise, interact, and become other field excitations almost immediately. Yet brief does not mean unimportant. The W boson's field nature is exactly what allows it to be so widely connected. Because it is a quantum of the charged weak field, it can appear wherever weak charged current processes are allowed. It can mediate beta decay in old stone. It can help turn a proton into a neutron in the sun's core. It can let a neutrino finally touch matter inside a deep detector. It can appear as a real particle in the controlled violence of a collider and then vanish into leptons or quarks. One field, many settings. The same answer also gives the W boson a quiet unity. Its behavior in a radioactive nucleus and its behavior in a collider are not separate identities. In one case, it is virtual, an intermediate contribution inside a low-energy process. In another, it is real, produced on shell, with its full mass before decaying. The distinction matters for measurement, but the underlying field is the same. The W boson is the name given to that field's charged quantum when it participates in nature's weak transformations. There is a deep stillness in this picture, even though the particle itself is short-lived. Space is filled with fields. Most of the time, the weak field does not rise into a real W boson. It remains part of the background possibility of the world, present in the equations and in the allowed interactions of matter. Then, under the right conditions, a disturbance appears. It carries charge. It changes a quark's flavor or decays into lighter particles. It is gone almost before time can be divided. The field remains. So, the W boson is not a tiny object made from hidden material. It is not a small bag of quarks, nor a compressed knot of ordinary matter. It is a quantum event of the charged weak field, made heavy by the Higgs field, made short-lived by its many allowed endings, made meaningful by the transformations it carries. Its substance is not substance in the old sense. Its reality is field, symmetry, charge, mass, and interaction. In that answer, the story returns to the still matter where it began. A stone rests in darkness. Water lies clear in a glass. The sun pours light across a sleeping world. Beneath these calm forms, fields remain active. A neutron may change. A proton may change. A neutrino may pass through Earth and leave no mark, or once in a great while, leave one faint trace. The W boson does not wait inside these things like a hidden grain. It appears only as the weak field briefly rises to carry transformation. Then it fades, leaving matter changed and the field silent again. The W boson leaves a story that does not end inside the particle itself. It begins with a small charged transformation and spreads outward into the structure of the world, not as a visible thread, but as a hidden rule repeated in many places. A quark changes flavor. A neutron becomes a proton. A proton becomes a neutron. A nucleus shifts its identity. A star finds the slow pace of its burning. A neutrino touches matter only rarely. The early universe settles into a balance of hydrogen and helium. Each scene is different in scale, yet the same weak doorway appears within it. There is a calm order in this. The weak interaction is not loud. It does not shine across space like electromagnetism. It does not gather planets and stars through gravity. It does not bind quarks with the strength of gluons. It works in the small places, in the private distances of particles, where the difference between one form of matter and another can be carried by a boson that exists for less than a measurable breath. It is a force of thresholds. It does not move matter far. It lets matter cross from one identity to the next. That makes the W boson easy to overlook and difficult to replace. Without it, neutrons could not decay in the familiar way. Certain unstable nuclei would have no path toward the forms they naturally take. The carbon clocks used to read old wood and bone would not tick by the same rule. Potassium in ancient rocks would not help mark volcanic time in the same way. The quiet background of beta decay, spread through stone, atmosphere, water, and living tissue, would have another shape or no such shape at all. The sun would also be changed. In the core, where hydrogen nuclei press through heat and density, the first step of the proton-proton chain needs the weak interaction. One proton must become a neutron. One up quark must become a down quark. A W+ boson must carry the charge of that transformation, even if only as the briefest intermediary. Because the step is rare, the sun burns slowly. Its light is not a sudden release, but a long patience. The heaviness of the W boson helps turn nuclear fire into a stable dawn that lasts across billions of years. This slowness is part of the habitability of a world like Earth. A star that burns steadily gives planets time to cool, atmospheres time to form, oceans time to gather, chemistry time to become complex, and lifetime to explore its own possibilities. The W boson does not intend any of this. Physics has no need for intention in such a place. The connection is enough. A short-lived carrier in the solar core helps regulate a star, and a regulated star becomes part of the long environment in which a living planet can remain warm. In the early universe, the same interaction helped decide how many neutrons survived long enough to become helium. Before stars, before atoms, before the dark spaces between galaxies became transparent, protons and neutrons changed into each other through weak processes. As expansion cooled the plasma, those changes slowed and froze into a ratio. That ratio shaped the first nuclei. Most ordinary matter remained hydrogen. A large share became helium. The universe carried that first composition into the age of stars. The W boson, therefore, belongs to both the beginning and the ongoing maintenance of visible matter. It helped set the early inventory, then later helped stars use that inventory. It does not sit at the center of the universe as an object. It is not a jewel hidden inside space. It is a repeated permission written into the fields. When the conditions allow it, the charged weak field rises into an exchange, and the exchange changes the story of the particles involved. The Higgs field gives the W boson the mass that makes all of this narrow and slow. Without that mass, the weak force would not be weak in the familiar sense. It would reach farther. It would act more readily. The careful delays built into nuclear processes would be altered. The separation between electromagnetism and the weak interaction would not look the same. The world of atoms, stars, decay, and chemistry would not carry its present rhythm. The Higgs field itself remains unseen in ordinary life, but its background value fills space. It is not a fog that can be blown away, not a substance with an edge, not a medium through which ordinary objects swim in the old mechanical sense. It is a quantum field with a non-zero value in the vacuum, and its relation to the electroweak fields gives mass to the W and Z bosons while leaving the photon massless. This is why one force reaches across the sky while the other reaches only across the smallest inner spaces of matter. The photon and the W boson become two kinds of fate. The photon can carry light from a galaxy so far away that the light began moving before Earth had its present continents. The W boson cannot cross the width of a proton before it is gone. Yet the shorter life does not make it less real. A long road and a narrow doorway can both shape a house. The photon fills the universe with visibility. The W boson permits transformation where visibility cannot enter. This difference also changes the meaning of emptiness. Space is not merely the absence of things. It is the place where fields have values, where symmetries may be hidden or broken, where particles can appear as excitations when energy and rules allow them. A vacuum can hold the Higgs field. It can hold the possibility of photons, electrons, quarks, gluons, W bosons, and Z bosons. It can look empty to the eye and still contain the underlying grammar from which interactions arise. The W boson is one word in that grammar. It carries electric charge. It has spin. It couples to left-handed particles and right-handed antiparticles. It connects quark flavors across up-type and down-type families. It opens charged, weak current interactions for leptons and neutrinos. It decays into lighter particles with a width that records how quickly its possibilities are spent. Its known properties are not decorations around a tiny hidden object. They are the object as far as present physics can test. A field excitation has no need for inner gears. The search continues because physics is never finished, simply because a model works well. The standard model describes the W boson with great success, but it leaves questions beyond its own borders. Neutrino masses point to missing structure. Dark matter has not found a place among the known particles. Gravity remains outside the quantum framework that describes the other forces. The matter-antimatter imbalance of the universe is larger than the known sources of symmetry violation seem able to explain. The W boson sits inside the successful model, and also near the places where the model is tested most carefully. This is why its mass and width matter so much. A small difference in the W mass could suggest unknown particles affecting the electroweak structure through quantum loops. A width larger than expected could suggest unseen decay paths. Agreement with prediction is also information, because it narrows the ways new physics can hide. The particle itself lives almost no time at all, but the measurement of its properties becomes a long act of listening. The collider makes the event. The detector records the aftermath. Years of analysis turn the traces into a number. In the end, the W boson teaches a quiet lesson about scale. The smallest known interactions are not separate from the largest structures. The weak force helps determine how stars burn, how elements change, how neutrinos travel, how early matter settled, and how precision experiments test the edges of known law. A particle that cannot be watched directly can still influence the light of a star. A field excitation smaller than any image can still help set the time available for planets and life. Matter, seen from far away, keeps its calm surface. Stone, water, air, skin, and starlight hold their familiar forms. Beneath them, fields remain present. Most atoms do not change in any noticeable way. Most neutrinos pass without touching. Most protons in the sun scatter for ages before one crosses the weak doorway. The universe is full of almost events, near chances, rare openings, and long waiting. The W boson appears only when the door opens. It does not stay. It carries charge through a transformation, spends its mass energy through allowed paths, and disappears into the particles that remain. Its life is too short to become a journey. Its effect is large enough to become part of cosmic history. In that contrast, the particle finds its place, not as a lasting thing, but as a brief permission for matter to change, written into the field structure of the universe. The story settles back into the present, where matter keeps its familiar calm. A stone remains beside the path. Water rests in a glass. The night air gathers softly around windows and roofs. The great fields of physics do not need to be seen in order to remain there, filling the quiet spaces between atoms, holding the rules by which light travels, stars burn, and small transformations pass through matter without sound. The W boson has already faded from the scene. Its life was never meant to linger. It rose only as a brief motion of a field, carried charge through a hidden change, and disappeared into lighter particles. What remains is not the particle itself, but the world shaped by such small permissions: stable atoms, slow stars, old rocks, passing neutrinos, and the faint order of elements beneath every surface. Above the sleeping Earth, the sky keeps its dark patience. Photons from distant stars cross the open black. Neutrinos pass through oceans and mountains without stirring them. In the sun, deep below the bright surface, rare weak steps continue in the pressure of the core, one after another, slow enough to let daylight remain gentle across long ages. Nothing hurries there. Nothing needs to be held. The mind can let the image soften now. Fields lying everywhere. Space not empty but quiet. matter resting in forms that have taken billions of years to become familiar. The smallest changes continue far below thought. The stars continue their measured burning. The night continues to deepen. And in that dark, the universe does not need to be solved. It can simply remain, vast and silent, while the body grows heavier, the room grows softer, and every hidden field keeps its ancient rhythm beneath the calm surface of sleep.